Hi, we are still investigating powers of trigonometric functions. In case 5, we will examine odd powers of tangent. You would only use techniques that will be presented in this video if you've checked that the integral is not basic, that substitution and integration by parts fail, and that algebraic methods are also unsuccessful. Odd powers of tangent cases can be recognized by tangents whose degree is odd, either alone or combined with secants. So how does the method work? We're going to use tan cube of x as a guiding example. In step 1, factor out a secant x tan x term and associate it to the dx. Now this may seem odd, especially in our example where there is no secant x to be factored out. Therefore, there are situations where you may have to create a secant x of your own. In our example, that could mean multiplying above and below by secant x. So, we were saying earlier that we need to factor out a secant x tangent x term. We can now take one of the tangent x's from our numerator and join it to the secant x that we've created. Step 2, use the identity tan square x plus 1 equals secant square x to replace all the remaining tan square x's by secant square x minus 1. In our integral, tan square x remains at the numerator within our integrand and can therefore be replaced. Step 3, apply the substitution u equals secant x, whose du is secant x tan x dx. In our integral, notice how every single term can be either associated to secant x, which is a u, or to secant x tan x dx, which is going to become a du. And the resulting integrand would be a combination of powers of u. In step 4, complete the antiderivative by using expansion or by splitting the numerator and return to variable x. In our case, we will split the numerator and use the power rule to integrate u and recognize that 1 over u is actually a ln function when antidifferentiated. Finally, we can return to x's by recalling that u stood for secant x. If the integral has bounds, adapting the bounds as you go along is a useful way of avoiding having to return back to x's. In the second example, we'll look at the odd tangent case, secant to the power 3x, tan to the power 3x dx, that comes with bounds 0 to pi over 3. In step 1, we have to pull out a secant x tan x combination along with the dx. This means we are only leaving secant square x and tan square x behind. In step 2, all remaining tan square x's can be replaced by secant square x minus 1. Once again, recall that the derivative of secant is secant x tan x dx, which justifies the next step that will come. Replace all secant x's by u and observe that secant x tan x dx is the right du. As we progress with our substitution, we can also adapt the bounds. The lower bound, x equals 0, has a corresponding value for u, which is secant 0 equal to 1. The upper bound, pi over 3, has a value for u of secant pi over 3, which happens to be 2. Replacing all of our variables and bounds, our new integral in terms of u is a combination of powers. We can then distribute those powers and apply the power rule to finish the antidifferentiation process. And the remaining term is to do our computations.